Oh yeah, I'm Abdelouahed Ouardghi, and please call me Abdel. So I'm a postdoc in UNISH, and today I'm going to talk about my work about the parallel in time spectral deferred correction methods for fluid simulations. So let's start with acknowledgement for the project I'm working on, the Strömungsraum. So briefly, this project is the aim of this project is to adapt the CFD applications to the upcoming exascale machine using advanced algorithms that can benefit from the peak performance. And in this project, there is 6 partners, and we, UNISH, our goal is to develop parallel in time for parallel in time codes for fluid simulations. So in this presentation, I will explain the spectral deferred correction method, starting from a collocation, the collocation problem to the actual SDC method, and then I will talk about the semi-implicit version of SDC, and then how we can parallelize SDC, and I will talk a little bit about the software I used, and then I will give some or share some numerical results and end up with a summary. So as I mentioned at the beginning, our goal in FZG UNISH in JC is to develop parallel in time integrators for fluid simulation. So now, why we use SDC? So SDC is an iterative method that can use a low order time scheme and deliver high order solutions, and we can achieve this by performing a series of corrections at each iteration. So to explain this, let's start from the classical initial value problem. So here I'm limiting the calculation to a one time step interval just for simplification. And now, in order to explain this, the first thing we need to do is to rewrite our problem in a Picard form. And then what we can do is that we can subdivide the time interval using or by defining a set of nodes. And then we can approximate our function f here using the Lagrangian polynomials. And then since we have this approximation, we can then go and approximate our Picard form. The integral can be approximated like this, and then we have here the solution. This is at each node 2m, we have the solution, and here we have this is the initial solution bringing forward from the last time step, and here we have this q emg are the weight of the method and are defined by the integrals of the Lagrangian polynomials. And since this equation is valid for all nodes, we can write them together in one matrix vector system. And now we have this collocation problem, and which is equivalent to the fully implicit Range-Kutta method. And yeah, also I can mention here that the explicit and the diagonal Range-Kutta method can be seen as a collocation problem. And for these two methods, by using these two methods, we can avoid solving all at once system, and that means we can solve our system by using the forward substitution. Now, this collocation problem, again, it's generally dense and hard to solve. So either we can solve it using a direct solver, the thing that we don't want to do, and then we need to find an iterative solver. And this is why the SDC, so here, this is just like an arrangement to this equation. So we have now right hand and left hand side. So here, in order to solve this equation using the spectral deferred correction method, so we introduced SDC as an iterative method here, and here it is like an explicit iteration. So then, in order to increase the range and the speed of the convergence, we do preconditioning. So the idea here is to choose a preconditioner that it is easy to invert, but it is like a best approximation of our system operator. In SDC, what we do, we take this operator as a preconditioner, with the difference that here the Q delta is the new approximation of our integration matrix Q. And in order to avoid solving all at once system, here what we do, we choose Q delta to be a lower triangular approximation. And by doing this, we can, as I mentioned before, we can solve our system like using forward substitution. And now just arranging our equation. And now this is an example of the Q delta or the preconditioner. So usually in the SDC, we use the LU trick to create the Q delta from our integration matrix Q. And then the iteration at each node can be written like this. And if you look here, this is just a quadrature, and this is the correction step here, the correction step. And since we are using the lower triangular matrix, we have only here one term that make it implicit. So we can solve it like this. Then we can use also explicit SDC. So for explicit SDC, we force our Q delta to be strict lower triangular matrix. And again, we have a quadrature term and a correction term. Now, for the what is next, so we can combine the implicit and explicit, so to do an IMEX SDC method. So when we have our equation has two parts, one part it is like stiff and the other part is not stiff, we can use IMEX SDC. And for IMEX SDC, we just replace this term, the Q delta, by multiplied by the function by this one. So we have here Q delta for the explicit part, and we have another Q delta for the implicit part. And here, both of them are lower triangular, but this one is strict lower triangular, so we can use it explicitly. And yeah, again, here we have the same iteration, which made of quadrature term and the correction term. And now, if we want to talk about the parallel SDC, so SDC can be parallelized across the methods. So we have for SDC, we introduce like a number of nodes, and then so in SDC, the number of nodes is equivalent to the number of stages in Ouardghi method. But here, the difference that the SDC is an iterative method. That means for every node, which is equivalent to a stage in Ouardghi method, then we have an iterative process. So what we can do, or what we need to do, because we don't want to increase the computational costs, what we can do is to do the calculation at each node in parallel. So in order to be able to do this, we need to use diagonal preconditioner. So let me go back a little bit here. So in this equation here, you can see that the iteration at each node still depends on the iterations from the previous nodes. But if we use a diagonal preconditioner, here we have only diagonal. That means here we will have only one term. So, and this term will not depend on the previous nodes. So this is what we have here. So if we choose the Q delta to be diagonal, then we have only one term here, and then we still have implicit SDC, but independently on the other nodes. So then, as examples for diagonal preconditioners, we have the diagonal implicit Euler, which is the simplest one. It's made of the nodes. We just subtract the initial time. And for others preconditioners, there is the preconditioner based on the minimization of spectral radius, and we have two of them, one for non-stiff problems and one for stiff problems. And for more information about the diagonal preconditions, I refer to the paper by Gayatri Chakolovic. This is a preprint still, but you can find it in archive. Now, let's talk about the software. So the software I'm using for the space discretization, I'm using finite element method implemented in Phoenix. And I don't think Phoenix, I mean, it's now, so I don't think that I have to talk about Phoenix, but here I would like to talk about PyACC. So PyACC is a Python code for ACC, and it is open source, it is well documented, and it is written in with a lot of tutorials. So anyone who is interested in SDC can use this one. There is many tutorials there, so I think it should be easy to adapt the code to your problem. Now it came the first test. So the first test I want here to test the IMX SDC or SI SDC. So here I solved the convection diffusion equation with for Gaussian Hill problem, and I used I used 3 nodes, and SDC 3 nodes is equivalent to the 5th order because the order is 2n-1. So here we were seeking the 5th order, and as you can see here, so by when using a well-refined mesh, we got the 5th order in time, but for the other mesh, so the error, the space from the error still dominate the time errors. Okay, so the next problem is the well-known benchmark of flow around cylinder, and the government equations here are the well-known incompressible Navier-Stokes equations with equipped with boundary conditions. And here I have to mention that the inlet or the inlet velocity is time dependent, which is a little bit hard to handle for this type of problems. So before going to STC, so then the easiest way to go with Navier-Stokes equation is to do a projection scheme. Here I'm showing the easiest projection scheme, the first one by Corins. So for the projection scheme, we have to decouple the velocity and the pressure, and then we solve for an alternative solution for the velocity. Then we do the projection to get the pressure, and we do at the end a correction to correct the velocity again. And here I used the SDC to solve this equation only, but even if SDC is used to solve this equation only, so these 2 equations needed to be solved at each iteration. Okay, here I'm showing the lift coefficient using different SDC methods. And when I say different SDC methods, that means different number of nodes. And the results are compared to the data provided by the Fateflu team from Dortmund. And yeah, the reference solution is in black. And I used half of the degrees of freedoms that Dortmund people use. And here I used 2 different time step size. So let me go for our zoom. So here in the solid lines, I have SDC method with different number of nodes, but using the same time step size used by in the reference solution. And you can see that, yeah, it's the solution, we can say that fit with the reference solution, but we cannot see that improvement because, as I mentioned, increasing the number of nodes should increase the order. And when I used a time step a little bit larger, okay, you can see here just using 2 nodes, which is equivalent to the 3rd order, the solution is a little bit shifted. But again, increasing the number of nodes bring the solution back to be fit with the reference solution. Next, we want to test okay, so next we need to test the preconditioner. Here I choose 4 time points. So here, because there is nothing here, and here where this shading after the cylinder start to develop, here and here. And what we do, we just compute the number of the average number of iterations at each point here. And we can see here that we still have the LU, the implicit Euler, and the two preconditioner from minimization, the spectral radius. And here, to be quick, so if we use this preconditioner, we don't lose anything. We can use the diagonal preconditioner because it's need the same number of iterations. That means we don't lose anything by using the diagonal conditioner, but using the Euler implicit, yeah, maybe we need the double of the time needed for the LU. Now, we wanted to explore again the fully implicit scheme for Navier-Stokes. So here I'm showing this is a semi-discretized version of Navier-Stokes. So in bracket, we have matrices, the finite element matrices. And if we see this equation, we can see the differential algebraic equation, the semi-explicit version of the IEs. And for this equation, we need a different type of STC. Yeah, we did it, but we prefer to go with the regular STC I explained in the beginning. So for this, we just rewrite the system in a matrix vector system. And again, I have this equation. Yeah, if for this matrix is not invertible, but since I'm using fully implicit, so one term from here will move to this side, and then I will have invertible matrix again. Let's move to the results. So here I'm presenting the result for STC, but here I'm using time step, which is 64 times larger than what I used before, or what the people from Dortmund used before. And I also tested against different number of nodes. And yeah, we can see that the solution is fit with the solution. So the thing I would like to say here that the results I showed you before, because I still run the code in serial, not in parallel. So the code go from days to hours. So the codes before were running like in 7 days, because I have almost 13,000 time step with a lot of iterations. But here I have maybe, I don't remember, but maybe 200 something time steps. So it's maybe just 2 hours something. And here again, I checked the preconditioner, the diagonal preconditioner. So one of them didn't work for non-stiff problem, because now I'm using large time step, so it didn't work. But using the same preconditioner again, it need the same number of iteration, and that means we can use the diagonal preconditioner for this type of problems again without losing anything. And yeah, for what we can take home from this presentation, that the STC method, it is an iterative method that can use low order method, such first order Euler method, and then give a high order solution by performing a series of correction. And also the STC can be used in parallel across the method. And yeah, for our next work, we are going to analyze the speed up of the code, and also we need to integrate by ICC with fit tree toolbox from the Dortmund in order to perform space-time parization. And thank you for your attention.